Hello and welcome. Have you ever really stopped to think about how your computer or your phone actually, thinks? It all boils down to a set of rules that are so simple it's almost unbelievable. It's like a secret language, and today we're going to learn how to speak it. So let's just start with this big question. At their absolute core, computers only get two things: on, which we call a 1, and off, which we call a 0. That's literally it. So how on earth do you get from a simple on and off to something complex enough to stream a movie or even fly a spaceship? Well, the whole secret is in these tiny little things called logic gates. You can think of them as microscopic decision makers. They take in those simple ones and zeros and, based on a single, simple rule, they spit out a brand new 1 or 0. That's the whole game. All right, so if we're going to learn this language, we have to start with the alphabet. And for digital logic, the most basic letters are the not, the and, and the or gates. Let's meet them. First up is the not gate, which sometimes gets called the inverter. It's the simplest one, and it does exactly what you think it does. It does the opposite. You give it a 1, it spits out a 0. You feed it a 0, you get back a 1. It's like a rebellious light switch that's just programmed to do the reverse of whatever you do. Now, to see how a gate behaves, we use a simple little chart called a truth table. It just shows you every possible input and what output you'll get. And for the not gate, it's super clear, right? Input 0 gives you an output of 1. Input 1 gives you 0. Simple as that. Okay, next up is the and gate. I want you to think of this one as a really strict bouncer at an exclusive club. It's got two inputs, and it will only, and I mean only, give you a 1 on the output if input A and input B are both 1. If even one of them is a 0, sorry, you're not getting in. And its truth table shows you exactly what I mean. Look at all the possibilities. A 0 in either input or both, and the output is a 0. It's only that very last row, where both A and B are 1, that we finally get our output of 1. It is truly an all or nothing situation. And our last basic gate is the OR gate. Now, if the AND gate is the strict bouncer, the OR gate is the total opposite. It's your super inclusive friend. This gate will give you a 1 if input A or input B is a 1. It doesn't care if both are 1, it just needs at least 1. Kind of like a house with 2 doorbells. Press either one, and it's going to ring. Let's check out its truth table. You see, the only possible way to get a 0 out of this thing is if both inputs are 0. Any other time, if there's even a single 1 coming in, the output is a 1. That flexibility is a game changer. So when you put them side by side, the difference is just crystal clear. The AND gate is strict, right? It's like an old string of holiday lights, wired in series. One bulb burns out, the whole thing goes dark. The OR gate is flexible, more like a modern parallel circuit where the other lights stay on. That one simple difference is pretty much the foundation of everything. Okay, so we've got our alphabet, not, and or. But how do you combine them to write complex sentences? Well, for that, you need a set of rules, a grammar. And in the world of digital logic, that grammar is called Boolean algebra. Now, Boolean algebra sounds kind of intimidating, but its purpose is actually really straightforward. It's all about efficiency. It's a system of math that lets engineers take a really complex logical idea and simplify it, boil it down to its essence. The goal is always to get the same result, but by using fewer gates. That makes the final circuit smaller, faster, and way cheaper to make. And hey, don't just take my word for it. As the textbook Foundations of Digital Circuits puts it, these exact laws are what facilitate efficient circuit design and analysis. It's the secret sauce that turns a messy idea into an elegant piece of technology. Okay, so this is all great in theory, but how does an engineer actually go from a real-world problem to a physical, working circuit? Well, there's a pretty clear path they follow. It really is a step-by-step process. First, you define what you need to happen. Then, you make a truth table for all the possibilities. Step 3, you write out a logic function from that table. But now, here comes the magic trick. Step 4, you use Boolean algebra to simplify that function, to make it better. And only then, at step 5, do you actually build the circuit. That simplification step is everything. So now, let's zoom out. We've seen the individual bricks, the gates. We've seen the architectural blueprint, Boolean algebra. Let's see what happens when we start using them to build entire cities. The way we do this is by creating multi-level logic circuits.
All that means is we connect the output of one gate into the input of another, and then that one into another, and so on. By chaining these simple decisions together, we can make them work together to do incredibly complex things like adding numbers or even rendering a character in a video game.
So, just how complex are we talking? Well, a modern CPU, the brain inside your computer, has somewhere in the neighborhood of 30 billion transistors. And every single one of those acts like a tiny switch, forming the very logic gates we've just been talking about. 30 billion. But here's the part that just blows my mind. Despite that staggering number, every single one of those 30 billion parts is still just a simple little decision maker, following the exact same and, or, and not rules we learned today. It's the ultimate example of immense, incredible complexity being born from profound simplicity. So there you have it, from just 3 simple concepts, this and that, this or not this. We've literally built our entire modern world. It is a language of pure, unadulterated logic, which really only leaves one question. What are we going to command it to build for us next?